Lesson 11-2, rational functions, and we are dealing with expressions, rational expressions today. So no equations, just expressions. Our objective is to identify excluded values and identify and use asymptotes. The standard Algebra 1 7.1 dealing with rational expressions. First of all, definition. A rational expression is an algebraic fraction whose numerator and denominator are polynomials. Polynomials cover a whole variety of things. Remember, under the umbrella of polynomials, there are monomials, binomials, trinomials, and so on. And remember, under the umbrella of monomials, it can be a plain number, or a variable, or a product, but I want you to be aware it can be just plain simple numbers, okay, but they're going to get much more complicated than plain simple numbers. Okay, so that's what a rational expression is. Polynomial over a polynomial. Now, what happens when you have something like 2 over 0? Well, if you do it in a calculator, you're going to get an error. Hopefully you all know that we cannot divide by 0. That is completely impossible. And you can never have a 0 in a denominator. Last week we talked about assume that no variable equals 0. Do you remember me talking about that? Okay, that went along these lines. When we were doing all those problems, you can assume that no variable was 0, because if they were 0, there couldn't have been a problem. It would have been impossible to solve. So we are now going to take that away, that assume no variable is 0, and they're going to have you figure out what's called excluded values. And what that means is what values for x would make the denominator 0. So you're thinking, okay, I don't want the denominator to be 0, so what would make it be 0? That's the number my variables cannot be. What you will do to find excluded values is you take that denominator, you set it equal to 0, and you solve it. Whatever it comes out to be, you say, those are the values my variable cannot be. Okay, so you don't just say it's going to be 0. That's not how we do it for these problems. They're going to be something else. So when we look at these examples, the first one, 3x minus 2 over x plus 7. Definitely a rational expression. It's a binomial over a binomial. But all we are looking for with this is the excluded value. So that means I am going to take x plus 7 and set it equal to 0. That's all you do. And you solve that equation. You want to know what x is? Well, we all know subtract 7. X is negative 7. So your excluded value would be negative 7. So when you did that problem, you would say that x could not be negative 7. All right, number 2, a little more complicated. 6a squared plus 2 over a squared minus a minus 12. Ben, do you have a question?
Yeah. But we have to write x cannot be 7.
You're going to write that x is not equal to 7, or negative 7, I mean. Or it's going to ask you actually to state what the excluded value is, and you just say x equals whatever. X equals negative 7. Okay? And the thing is, you got to understand that that's what you really don't want x to be, right? That's why it's called the excluded value. You really don't want it to be that. If it's that, it messes everything up. But when they say state the excluded value, you say x equals negative 7. All right, next, a squared minus a minus 12. Okay, so you set that equal to 0. All right, now, how do we solve a quadratic? We've had a whole chapter of this. What do I do? What? Factor. So a squared minus a minus 12, there's no greatest common factor in those three terms. 12 is not a perfect square, so it's not going to be a perfect square trinomial, so I set up my two sets of parentheses, set it equal to 0. What gives me a squared, Josh?
4 and 3. Oh,
A and A. Then this minus in front of the 12 means what about my signs? That they're different. And then you look at your factor pairs of 12. So 1 and 12, 2 and 6, 3 and 4. We want the pair whose difference is 1 because of this. So that would be 3 and 4. How do I know which one's going to go where? This is really important. Avery?
The one in front of the whatever number.
You got it. Whatever.
Negative in front of the second A.
Right.
Then the big thing.
That's exactly right. The sign in front of my A term is minus. It's negative. So that means my bigger number has to go with the negative. So it's going to be 3 and 4. Good job. So now I set each one of these equal to 0 and solve them. So in this case, there's going to be 2 excluded values. So it can't be, or it's going to, your excluded values are negative 3 and 4. Yes? If the equation was prime, I don't believe they're going to give you that. I don't believe you're going to.
What would you do though if it is?
Well, then you have to, okay, that's going to come up in very soon, how to solve a quadratic that is prime. Okay, it's called the quadratic formula. So, believe it or not, every equation, prime or not, is solvable. So, quadratic formula we will use, but we haven't had that yet, so it's not going to happen yet. So, in the future it could happen, but not now. Okay, good question. All right, last but yes.
What if the denominator is just x? Would it be x equals 0?
Yes, if the denominator is just x, then x equals 0. Yes. Nope, you don't have to put that in a solution set. Just negative 3 and 4. Okay, anybody else?
Could you put in a solution set though?
You could, yeah. It's really not a solution though.
Yeah.
It's the excluded values. So I'd kind of maybe steer clear of that. It's really not a solution set. It's
So the
just
answer would you just put,
I would just leave it just like that. Just leave it just like that. Okay, anybody else? All right, 8 over 2x plus 1. So 2x plus 1 equals 0. And subtract 1. 2x is negative 1, and then divide by 2. So x is negative 1/2. So x is negative 1/2. Questions about that one? All right, let's go on then. So that's excluded values. That's kind of half of what we're doing today. The other half talks about graphing these rational functions. And we have to introduce a term called an asymptote. And that is a line that the graph of a line approaches, graph of a function, that should really say, a line that the graph approaches, it never really crosses over it. And there's reasons why there are asymptotes. So let me kind of explain what the reasons might be. So your rational function that you're going to have would be in this format. Okay, this right here. Y equals something A over x minus b, and then possibly a number, a constant or something at the end. This over here, I would like for you to think of maybe as a y, not really a y-intercept, but kind of a y-intercept, just like in y equals mx plus b. And I'll tell you why in just a second. So this is going to be the way the format of the rational functions. It's going to be kind of crazy looking. There's going to be a fractional part, and possibly this number here at the end. Okay, now a vertical asymptote would be where the denominator of that fraction is 0. So you would set that denominator equal to 0 and solve it. Whatever that value is, that's where the vertical asymptote is. That means where it's undefined, it can't cross there. That's why you set the denominator equal to 0. It's where it's undefined. You can't cross there. Okay, now, if there is a number at the end, then you would say your horizontal asymptote would be where y equals c. Okay? So, whatever number that is, the y is going to be a horizontal line at y equals c. Now, if there's no number at the end, what number should you assume is there? 0, and therefore your horizontal asymptote would be at y equals 0, and we're going to see that here in just a minute. So right now, we're going to try to get this in, and then we're going to skip to where I said we're going to have a guest teacher showing you how to graph some of these. But right now, we're going to name vertical and horizontal asymptotes for each function. So example 4 down there, I've got something pretty basic. Y equals 2 over x minus 4. So for this one, the vertical one is where you set the denominator of the fractional part equal to 0. So the vertical asymptote would just be x equals 0. The horizontal would be the y equaling the number at the end. And for this one, what would that be? Negative 4. That's it for what we're doing right there. We're going to graph some in just a second. Okay, number 5. The vertical would be, you would say x minus 3 equals 0. And then add 3. So the vertical asymptote on this one would be 3. And what would the horizontal asymptote on that one be? Y equals what? Is there a number at the end? 0. And then finally, number 6, the vertical would be taking x plus 2 equaling 0. And what is my vertical asymptote then? X equals negative 2. And y equals 1. So that is just finding... that's finding the vertical and the horizontal asymptotes. Now we're actually going to check out the graphing of them.